Hello everyone, myself Pankil Shah and you are studying the subject Basic Electrical Engineering. And in today's video, we are starting a new chapter, that is the module 2, and it is three-phase AC circuits. So basically in previous videos we have seen single phase AC circuit, but in this video we are going to discuss some three-phase AC circuits. And in this three-phase AC circuit there are so many topics and that we have to cover in this video lecture series. So in today's video we are going to study about the generation of three-phase AC voltage, how three-phase AC voltage is generated. So let's begin with the three-phase AC circuit chapter. So first, let's discuss the important topic of this three-phase AC circuit. So in this video lecture series, in three-phase AC circuit, we will first discuss the introduction, or you can say generation of three-phase AC voltage. Later on, we will discuss some interconnection of three-phase system with the three-phase load, and that interconnection is known as the star connection. Another method to interconnect system and load is the delta connection. And lastly, we will discuss the power measurement in this three-phase AC circuit. So let's begin with the first topic of this chapter, and that is introduction, and that is generation of three-phase voltage. We have previously seen that how single-phase voltage is generated. So in this video, you will see how the three-phase voltage is generated. So before starting with the generation of three-phase voltage, let's discuss some importance of three-phase system, and that are first, all electric power is generated and distributed in three-phase manner. No electric power is generated in single-phase manner. Secondly, one phase, two phase or more than three phase can be obtained from the three-phase unit. So we do not need to generate separate voltages. For example, if your requirement is single phase, then you do not have to generate single phase voltage. You only have to generate the three phase voltage, and from that three phase voltage you can carry single phase according to your use. So that is the second advantage of three phase. Third, uniform power transmission is possible. Power can be transmitted uniformly in three-phase AC system. Also, vibration of three-phase machines are very less. So in industries, we are using three-phase machines. Next advantage of three-phase system is the instantaneous power in three-phase system can be constant, not pulsating. We have seen the pure resistive circuit, pure inductive circuit, pure capacitive circuit, RL, RC, RLC circuit. But in each type of that circuit, power was pulsating. But in case of power was pulsating means power at some instant will become zero. But in case of three-phase system, power will be constant. So this is the major advantage using three-phase system. Next is the high power motors prefer a steady torque, especially one created by a rotating magnetic field. So high power motors need a steady torque, not a pulsating torque. So it is obtained by the three-phase supply only. Next is the three-phase system is more economical than the single-phase system, because we know that to generate a single-phase voltage, we must require a single-phase generator. If you want to generate three-phase individually, then you may require three individual single-phase generator, and which cost more than the single unit of a three-phase generator. So this is also known as the advantage. And the last is the amount of wire required for the three-phase system is less than the three single unit of the single-phase system. So these all are the advantages of the uses of the three-phase system in our daily to daily life, or you can say these are the advantages of using the three-phase system. So let's begin with the generation of three-phase system. So to generate electricity in three-phase manner, or you can say to generate the EMF or the voltage in three-phase manner, your generation of three-phase EMF may be required three important things. First important thing to generate three-phase EMF is the magnetic field. Without a magnetic field, or you can say electromagnetic field, electricity cannot be generated. So obviously you must require a magnetic field. Once you have a magnetic field, also you cannot generate electricity because you must have a conductor placed in that magnetic field. So the second most important thing that you must have is the conductor. And if you want to generate electricity in three-phase manner, then you must have a three conductors, or you can say three coils. And the third most important thing is that if you have a magnetic field, if you have a three conductors in that magnetic field, but still EMF will be not induced in that coil because there is no relative motion between that conductor and magnetic field. So you must have a relative motion between them. So in this way, you can produce the three-phase voltage. Now let's see how this three-phase voltage is produced. So according to Faraday's law that we have already discussed in that single phase generation unit. So according to Faraday's law, conductor cuts the line of flux and then a voltage will be induced in that conductor. So conductor must need to be rotated, or a magnetic field must need to be rotated. Either one of them should be in rotating and another one should be in stationary position. So the direction and the speed of that rotation is very important in generation of three-phase voltage. So you can see this figure. In this figure, we have seen one stationary magnetic field is there. Magnets are not rotated. But you can see that there is three coils, and that three coils are rotated in the stationary magnetic field. So in this way, you can induce EMF in that coils. And we are using this concept in three-phase generators, or this is known as the alternator. So basically, in three-phase generator, there are three coils inside that generator, and that three coils are placed by 120 degree from each other. So whenever that coils are rotated in the stationary magnetic field, EMF will be induced in that three coils. So in any three-phase generator, this is the very basic concept that the three coils at 120 degree from each other are placed inside, and the stationary magnetic field will be outside, and in that stationary magnetic field, if our coil is rotated, then EMF will be induced in all three coils. So if our coils are 120 degree apart from each other, so we can say that the EMF induced in that coil will be also 120 degree phase difference with each other. So here you can see in this figure there are three coils named as A1, A2, B1, B2 and C1, C2 are mounted on the same axis but displaced from each other by the same angle, and that is 120 degree. So you can see in this figure there are three coils A1, A2, B1, B2 and C1, C2. The three are connected together on the same shaft, on the same axis, but they are 120 degree apart from each other. So the EMF induced in that three coils will be 120 degree phase shifted by each other. So three coils are rotated in anti-clockwise direction in magnetic field. So let's say that when the first coil, that is coil A1, A2, if our coil A1, A2 is in position AB, and position AB is the standard position, this at 0 degree you can say that. So at 0 degree, or you can say at position AB, an EMF will induced in this coil is 0. So at this position AB, if our first coil is placed, then we can say that the flux linking with this coil is maximum, but coil is right now not rotated. So if coil is not rotated, then there is no relative motion between the coil and the magnetic field. So we can say that there is no flux changing with that coil, and that means zero EMF is induced at this point. But whenever this coil A1, A2 change its position, or you can say that it is rotating in anti-clockwise direction, then flux will start increasing or decreasing through that coil. So EMF will start increasing. So this was about the first coil. So we have taken this A1, A2 as a reference coil. So at the same instant, the coil B1, B2 was 120 degree behind that first coil. So the EMF induced in this coil is approaching its negative maximum value. EMF induced in the second coil was in the negative maximum value. And at the same time, the coil C1 C2 is 240 behind the first coil. The coil C1 C2 has passed its maximum value. So again, I am repeating that at this position AB, the EMF induced in the first coil is 0, but whenever this coil is rotating in anti-clockwise direction, then EMF will start increasing. Second coil B1 B2 has just about to reach its negative maximum value, and the third coil, that is C1 C2, has been passed through its positive maximum value. So at this position, this three position of EMF we can draw in this waveform. So the EMF induced in all the three coils are in equal magnitude and of the same frequency. So we can write the EMF equation of all these three quantity as the maximum value is same and the frequency is same. So we can write the equation like this. Let's say E1 is equals to EM sine omega t, because at that position 0 degree EMF was 0. So if you put sine 0, then it will be 0. Then we have to write the EMF induced in the second coil, and it is denoted by the E2, and it is given by the maximum EMF EM in bracket sine omega t minus 120, because at whenever the coil was at 0 degree, second coil was at some other angle behind the first one, so it will be negative minus 120. And for the third coil, it was 240 behind the first coil, so it will be minus 240. Or you can say E1 is equals to EM sine omega t, or E2 is equals to EM sine omega t minus 2 pi by 3. 2 pi by 3 is nothing but 120, and E3 is equals to E0 sine omega t minus 4 pi by 3. So this three equation is known as the induced EMF in three-phase coils, where EM, or you can say E0, is the peak or the maximum value of that induced EMF, where omega is nothing but the angular velocity of that coil, and t is nothing but the time. So this was the three equations of the induced EMF. Now let's see the vector representation of three-phase EMF and the phasor sequence. How these vectors have the sequence as first coil at 0 degree, second coil behind that, and third coil also behind that. So to understand it, the standard practice is the color coding. So how you can define this is the first coil, this is the second coil, this is the third coil. So the coil that you have taken as a reference is always given as the color red R. The second coil, which was behind 120 degree from the first coil, is given as Y, that is yellow color. And the third coil, which is enlarged, or you can say 240 degree from the reference, is given as the blue color. So that means R, Y, V. Whenever we are telling that this is R phase, this is Y phase, and this is V phase, so this is the standard notation. And the standard notation is R coil means it is the first coil, which is having the equation as EM sine omega t. If we are talking about the Y coil, then it is 120 degree lagging behind the first coil. And if we are talking about the B coil, then it is 240 degree behind the first coil. So one can easily understand which coil is generated induced EMF in positive direction first. So here we have represented red color, red phase for the A1, A2 coil. So voltage at A1, A2 coil is treated by the red, or you can say VR. For voltage in B1, B2 is treated as the yellow color, so it will be VY, and voltage in the third coil, that is C1, C2, is denoted by the blue color, blue phase, so it will be VB. So VR, VY, VB are the three phase voltages induced in these three coils. If you want to draw the vector diagram, then you can see here, this is a vector diagram. In this vector diagram, this is a red color, and we have placed this vector at 0 degree because we have started from here only. So this is the voltage in the first coil, or you can say voltage in A1, A2 coil, or you can say voltage in R phase. From this R phase, behind 120 degree, we have drawn the yellow line, and yellow line represents the voltage in the second coil B1, B2, or you can say voltage in the second phase, that is the yellow phase. And from this, another 120 degree is located, and this is the blue line, and this is the voltage of the third phase. So this is known as the vector diagram of induced three-phase voltage. Now let's see the waveform of induced three-phase voltage. So we have seen the equation of the voltage induced in the first phase, that is the R phase, is V E1 is equals to E0 sine omega t. So if you are putting 0 degree in that equation, then the red phase will be starting at 0 degree from here. If you are putting 90 degree in that equation, then sine 90 is maximum. So this A coil, that is A1 into coil, is reaching maximum. If you are putting 180 degree, then again it will be 0. If you are putting 270 degree, then it will be a negative maximum. And if you are putting 360 degree, then it will be completes its one cycle. But if you are putting 0, 90, 270 and 360 in the second equation, then it will be 120 degree lagging behind this voltage first, that is VR. So you can say that the waveform of the second color, that is the yellow color, will start 120 degree after the first coil is started. So first coil is started at 0 degree, but second coil's voltage in positive direction will be started at 120 degree after the first coil. You can see this 120 degree. And from this 120 degree, after 90 degree, that is 120 plus 90, at that degree it achieves the maximum value and it completes its cycle after the red has been completed. If we are talking about the blue line, that is the third coil, then its positive will be starting at 240 degree after the red line. So you can see this is 120 and this is 120. So this is total 240. So this blue voltage, that is the voltage in blue phase, B phase, is started after the 240 degree of the red phase. And it completes its full cycle after the 240 degree of completion of our red phase. So this is known as the waveform of three-phase voltage. So in this way, you can draw the waveform of three-phase voltage. Thanks for watching this video. In this video, we have seen the generation of three-phase voltage, its vector diagram and its phasor representation. Thanks for watching this video.